Farming looks peaceful until the machinery starts moving. A rice transplanter crosses flooded mud in perfect rows. A sunflower header takes 16 rows at once. Orchard machines shake a crop loose in seconds. And one machine can lift a mature tree straight out of the ground. Farm machinery cannot simply overpower what it touches. It has to work fast without crushing the crop. The harder that becomes, the stranger the machines get. Hedge trimming sounds simple until the tractor starts moving. The power is easy to provide. Keeping a cutting head at the correct height and position while it follows uneven living growth is harder. Modern trimming attachments can communicate with the tractor through an ISO bus, allowing cutting position, height, length, and speed to be coordinated from the cab. The operator can adjust the working geometry without treating the attachment as a completely separate machine. Afron takes the same job further, with extending arms that work both sides of a hedge during one pass. The tractor keeps moving down the row while the cutting heads maintain their position on either side. That saves a return pass and reduces the number of times the operator has to line the machine up again. Rice planting adds a much less stable working surface. A Korean rice transplanter operates in flooded paddies, where the tires or tracks are moving through soft mud, and the actual ground can be difficult to see beneath the water. Even so, the machine has to place young plants at regular spacing while maintaining a straight path across the field. The result is visible immediately behind it. Rows of seedlings appear in an organized pattern across ground, where walking alone can be awkward. That accuracy helps later operations. Spraying, fertilizing, and other passes become easier when the crop begins in predictable rows. Other transplanting machines automate the sequence workers would otherwise repeat plant by plant. The planting mechanism establishes the position and depth, opens the soil, guides the seedling into place, and firms the soil around the roots as the carrier continues along the row. The challenge is maintaining that sequence as speed increases. A seedling is light enough to bend or shift before the soil closes around it, so the feed system and planting mechanism have to stay synchronized with the machine's forward movement. Bulb planters take the process another step toward automation. In the Flemish system, bulbs travel through belts and rollers that separate, count, and feed them toward the planting mechanism before they are pressed into the soil at controlled depth. The operator keeps the machine supplied and on course, while the mechanism handles the repeated placement. Heavy equipment can force its way through rock and soil. A planter has a different requirement: move quickly without bending a seedling, disturbing its roots, or allowing thousands of small placement errors to accumulate across the field. Planting requires accurate placement. Harvesting has to maintain similar control while moving much more material. A 3-row carrot harvester works on a crop that is still buried in the ground. The machine engages several rows while moving forward, lifts the carrots, separates much of the surrounding soil, and transfers the crop into its collection system. The carrots have to survive that entire path. Extraction that is too aggressive can crack or bruise them, while a poorly controlled transfer can damage the crop after it has already been removed successfully. The Dana machine works on another delicate product and combines cutting, collection, and transfer into trays, while the operator manages the process from a joystick. Once the crop is cut, the path through the machine becomes important. Every conveyor transfer, drop, turn, and pinch point has to move the product without creating more damage than the machine saves in labor. Green onions show how mechanization can reorganize the workers rather than remove them completely. The machine lifts the onions and places them onto a conveyor. Workers riding on the platform can then focus on packing instead of repeatedly bending, pulling plants from the soil, and carrying them out of the row. Their effort is concentrated on the part of the job where hands still make sense. Automatic lettuce harvesting moves more of that work onto the machine. Verbruen's system cuts the heads and arranges the harvested product for collection, reducing the number of separate handling steps before the lettuce reaches a container. Fruit harvesting adds an even tighter constraint. An apple harvester using X16 technology is designed to collect fruit quickly, while limiting rough handling. Apples can be removed from the tree perfectly and still lose commercial value if they arrive in the bin covered in bruises. So the handling system has to control what happens after the fruit leaves the branch, not just the picking action itself. Then the filled containers have to leave the orchard. A box eater system can carry 22 harvest bins in one trip. That attacks a different part of the same operation, keeping empty bins available near the harvester and moving full ones away before they begin blocking the workflow. Once the crop reaches the yard, a Marco-type heavy loader handles the filled containers as freight. It has to pick them up, keep the load stable, move them quickly, and clear room for the next group coming out of the field. Harvest speed therefore depends on more than the cutting or picking head. The crop has to keep moving after it has been removed from the plant. If the conveyors, bins, loaders, or transport vehicles fall behind, the harvester eventually has to slow down as well. Bosch's Deep Field Robotics project introduced a different kind of agricultural problem. Bonyrob had to identify the plant before deciding what to do with it. The robot, roughly the size of a small car, used cameras together with video and LiDAR-based positioning and satellite navigation to move through the field with high accuracy. Machine learning algorithms analyzed characteristics including leaf shape, color, and size to distinguish crops from unwanted plants. That matters when the visual difference is small. Bosch used young carrots and chamomile as an example. To a casual glance, both can appear as small green plants in the same patch of soil. The robot still has to classify one as the crop and the other as something to remove. After identifying the weed, Bonyrob can position a mechanical ram over the target and drive it into the ground. That allows individual weeds to be treated mechanically instead of spraying herbicide across the entire area. The machine therefore has two separate jobs. First, it has to navigate accurately enough to know where it is. Then the vision system has to classify what is directly beneath it before the mechanical tool acts. That is a very different workload from a conventional cultivator that simply stays between known crop rows. Precision irrigation works without machine vision, but placement still matters. An 8-wheel Fiat Agri machine can position irrigation pipe between young plants using hydraulic control. The machine has to carry and place the equipment without allowing its own wheels or pipe handling system to damage the crop already growing around it. The FB Tulip irrigation system then manages variables such as hose length and pressure, so water can be distributed more consistently across the intended area. The engineering is less dramatic than a giant harvesting head, but the scale of repetition is the same. Any small mistake in positioning, identification, or water delivery becomes much larger once it is repeated across an entire field. Some agricultural machines become extreme because a particular crop leaves very little room for general-purpose equipment. Cotton harvesting shows what happens when width becomes the advantage. A large Brazilian cotton harvester works several rows at the same time, gathering the white crop through a wide harvesting head while continuing down the field. Every extra row covered in the same pass reduces the distance and time required to work the field. Hazelnut harvesting uses a different approach. Instead of relying on separate machines for every stage, large systems can combine shaking, collection, and loading so the crop spends less time waiting between operations. That keeps the harvesting sequence moving and reduces the amount of material that has to be recovered from the ground later. Sunflowers push working width much further. The Olimac Drago Gold is available in a 16-row configuration. On a Claas Lexion 8700, one 16-row setup covers roughly 12 meters across the front of the combine. That is a huge working face to keep under control. The header uses relatively slow picking chains with large rubberized blocks that guide the plants through the mechanism while reducing the violent shaking that can throw kernels away before they reach the machine. Under suitable conditions, working speed can reach roughly 12 kilometers per hour. The important detail is not simply that 16 rows fit across the front. All 16 have to enter a system that can keep feeding material toward the combine without creating losses faster than the machine can recover them. A wide harvesting head only earns its size if the crop actually makes it inside. Steep vineyards force engineers to solve almost the opposite problem. Width matters less when the machine is working on a hillside. As the slope increases, the machine's mass shifts downhill. Traction changes between the wheels, the chassis has to remain stable, and the harvesting system still has to keep handling the grapes while everything underneath it is operating at an angle. On flat ground, the operator can concentrate mainly on the crop. On a steep row, the machine also has to manage gravity. Peat equipment faces another difficult surface. The Mary Peat machine works in wet terrain, cutting peat into controlled sections and leaving rows of material positioned for drying and later handling. Soft ground changes the way the vehicle can move and support its own weight, so the machine and the harvesting method are closely tied to the environment. These machines look unrelated when parked beside each other. In the field, their shapes make more sense. The crop spacing, slope, soil condition, and harvesting method have dictated almost every important part of the design. Orchard machinery deals with a particularly difficult constraint. The machine has to remove the crop without destroying the structure that is expected to produce again next season. A trunk shaker makes that conflict obvious. The machine approaches the tree and closes a hydraulically controlled clamp around the trunk. Once the contact is secure, the shaker sends rapid orbital vibration through the wood. The tree moves violently enough to release the nuts, often within seconds. But the clamp cannot simply squeeze harder whenever the crop refuses to fall. Hydraulic systems can adjust the pressure applied to different trunk sizes, and some machines automatically maintain the grip while the shaking mechanism is active. Padding at the contact surfaces helps spread the load instead of concentrating it against a small section of bark. The vibration also has to transfer enough energy through the trunk and branches to release the crop without turning the operation into uncontrolled impact. For the operator, the useful result is obvious when the nuts fall. For the tree, the quality of that contact matters long after the machine has left the orchard. Berry harvesting requires much softer handling. The Jagoda Oscar 4WD uses picking heads that work around the row and release berries from the bushes while the machine moves forward. Depending on the crop and conditions, harvesting output can reach roughly half a hectare per hour, with collection accuracy listed above 95%. But one of the more revealing design details is measured in centimeters. The distance between the bushes and the conveyor can be kept below 10 centimeters. That short transfer reduces how far the berry falls after it comes free. For a hard agricultural product, another few inches might mean almost nothing. For a soft berry, it can be the difference between arriving intact and striking part of the machine on the way down. The harvested fruit reaches the conveyor quickly, while cleaning systems separate leaves and other unwanted material before collection. The machine still has to move at commercial speed. It simply has to control that speed more carefully than equipment handling grain, soil, or chopped biomass. Then Contec takes the same basic problem, working around a living plant, and increases the scale dramatically. The machine is designed to move the tree itself. A circular arrangement of large spades is positioned around the trunk. The blades drive into the soil from several directions and continue downward around the root zone. As they converge beneath the tree, they cut out a large root ball with the surrounding soil still attached. That soil matters. It supports the root structure and helps keep smaller roots protected during the move. If the root ball breaks apart during lifting, the machine can expose or tear away much more of the underground system than intended. Making the root ball larger protects more roots, but it also increases the mass the machine has to lift. So the spades have to enter the ground at the right geometry, meet beneath the tree, and hold the soil together as the hydraulic system raises the load. Then the entire tree begins to move. The trunk rises with the root ball locked inside the spades. Soil that had been part of the ground is now hanging from the machine, carrying the roots with it. Above that sits the canopy, which may represent years of growth. A conventional excavator could remove the tree much faster if survival did not matter. Contec exists because survival is the job. The machine has enough digging and lifting force to remove a mature tree from the ground, but the excavation has to finish with the tree intact enough to be transported and replanted. Earlier machines in this video were placing young plants into the soil. This one handles the same biological system years later. When moving it requires several tons of earth to come along for the ride. Agricultural machinery becomes extreme for reasons that are easy to miss from the side of the road. A planter may be fighting for inches of accuracy. Boney Rob has to identify one small plant among thousands. A 16-row sunflower header has to control crop flow across roughly 12 meters of machinery. Orchard equipment has to shake, lift, and move living plants without destroying the next harvest in the process. Which would you want to see working up close? Boney Rob, the 16-row Drago Gold, the orchard shaker, or the machine that moves an entire mature tree? Subscribe to Megamass for more machines built for jobs ordinary equipment cannot handle.